On this adventure, we're going to discuss fields. Alright, now we discuss fields. So, a ring is a field if the non-zero elements form an abelian group with respect to multiplication. So, you already get that it's associative because you already have a ring structure. But this tells you that you also have a unit and that multiplication is commutative. So this already tells you have a commutative ring with unit. But more importantly, it tells you that the elements have multiplicative inverses. At least the non-zero elements do. As we already discussed, division by zero doesn't make sense. So 0 can't have a inverse. So if you take that away, everything else does. One of the standard examples is the complex numbers, because we already showed earlier in the course that the non-zero complex numbers formed an abelian group. Another obvious example would be the real numbers. As a note on history, the word field comes from a mistranslation from a German word, which actually should have been translated as body. So of course one should ask, why do we care about fields in the first place? Well, way back in linear algebra, they discussed the concept of a vector space as a set where you could add and multiply vectors. And by multiply, it was scalar multiplication. It turns out the set of scalars have to come from a field. So in that class, usually the field is always assumed to be R or C, but it turns out all the theorems from linear algebra, except the stuff involving dot products, actually make sense for any field. And so a lot of the theorems work just fine. The notion of dimension, the notion of basis, all those types of results, eigenvalues and eigenvectors, etc., everything goes through. So a lot of theorems work just fine. And so in computer science, working over Z mod 2Z is a pretty common field to work with. So the fact that linear algebra still works in that setting is pretty important. Similarly, if you're studying systems of polynomial equations and trying to solve them, the best theorems we know all involve working with fields. In both cases, sometimes you need more structure, like you need to ensure that the field has certain types of solutions, what's called being algebraically closed, so like the complex numbers. In those cases, you can get better results, but at the very least, you usually need at least fields to get started. And in fact, a lot of the harder parts in pure math research involves trying to see what happens when you don't have fields, when you're looking specifically for solutions that are integers. That's, the famous Fermat's last theorem. The reason why it was so hard to prove is because it's a statement about non-existence of integer solutions to the equation x to the n plus y to the n equals z to the n, where n is bigger than 3. And that's a pretty hard statement because you can't use field structures at all, and that's what makes that proof so hard and why it took so many centuries to find it. So the point is, being able to divide is actually very useful. Alright, now let's look at another example of fields. Q adjoin the square root of 2. This is the set of all numbers of the form a plus b times the square root of 2, where a and b are both rational numbers. We claim this is a field. At this point in the course, I'm going to point out that there are two ways you could solve this, or prove this claim. The first would be to go through the effort of showing that this is in fact a ring, the hard way, and then show that the non-zero elements form an abelian group with respect to multiplication. So that's, for this part, that's 4 axioms, because you have to prove associativity, commutativity, identity, and inverses. More importantly, if you prove commutativity and associativity for multiplication for Q adjoin 2 total, then you now have most of what we need to get away with showing only one of the distributive laws. And if you remember, you don't have to show commutativity for addition here anymore, so you still have to show an additional 3 axioms for the addition structure. One thing I've always neglected to point out is that if your ring has a 1, it's enough to show that 1 has an additive inverse, because then our properties actually tell you that -1 times A is the inverse for everything else. So that's always kind of a handy thing to take advantage of. If you have a unit, then the additive inverses part is actually easier to prove, because you don't have to take an arbitrary ring element and find its additive inverse. You can just find the additive inverse of the unit. But either way, you still have 7 things to show. Approach 2 is to show that Q adjoin 2 is a subring of R. And then Q adjoin 2 take away 0 is a subgroup of R take away 0. Depending on the conditions you're using, if you're using the subring criterion, that's 3 conditions. One of the subgroup criterions would give you an additional 2, but there's an overlap there. So you have 4 things to show. So obviously we're going to go with approach 2. So let's use approach 2. First off, we need to show that this set is non-empty. Well, it contains the square root of 2, so we're good there. Next, we need to show it's closed under subtraction and multiplication. So we're going to take 2 elements in this set. We see that if you subtract 2 elements in this set and you group like terms together and factor out the common factor of the square root of 2 here, you get another element that's in this set that can be written as a rational number plus a rational number times the square root of 2. Likewise, if you multiply 2 numbers of this form and you FOIL properly, square root of 2 times square root of 2 is 2, and so you bring that up to the front, and you see that you can rewrite this expression as a rational number plus a rational number times the square root of 2. So this is in fact a subring. It is closed under multiplication and subtraction. And now we don't have to worry about associativity and distributive laws. So the only thing we're missing is the subgroup criterion. So we already have closure under multiplication because we just showed it. And we already know the set's not empty. Although I guess technically we need to work with things that are non-zero here. So then you do need to think about the fact that if these are both non-zero, then their product is non-zero. So that is a sanity check you do have to think about. Plus stuff times the square root of 2. And we notice that there's no subtraction going on here. And so as long as one term in each factor is non-zero, then you're guaranteed that one term in this product is non-zero. So yes, this is closed under multiplication. So then we just need to check that it's closed under inversion. So here's the inverse. As a real number, that's just the reciprocal. Let's multiply the numerator and denominator by the conjugate. And then simplify. The bottom becomes the difference of squares. The top just stays a minus b square root of 2. Now I separate out by the part that doesn't involve the square root of 2 and the part that does. And so that we see that we do in fact have inverses in this set. So it's closed under inversion. And so this is in fact at least the part where you take away 0 is a subgroup with respect to multiplication. Under multiplication. And hence, we do in fact have a field. So now we come to our first of two theorems about fields. This one is the easier of the two. Every field is an integral domain. So integral domains are more general than fields. So what we're going to show is that every non-zero element in R, we're going to assume R is a field, and we're going to assume every non-zero element is not a zero divisor. How are we going to show that? We're going to show that if you multiply that element by some other element and you get 0, then it must be the case that that other element was 0. So let B be an R and suppose AB equals 0. Well, since A is not 0, A has a multiplicative inverse, so we can multiply both sides on the left by A inverse. And A inverse times 0 is still 0. Multiplication is associative, so we can move the parentheses over. A inverse times A is the multiplicative identity. Multiplicative identity times B gives you the multiplicand back, which is B. And so we see that B is equal to 0. Therefore, A is not a zero divisor. And since A was an arbitrary non-zero element, none of the elements are zero divisors. Hence, R is an integral domain. There are two other facts you need. You need remember that R has to have a multiplicative unit. Oh wait, it already does, because since R is a field, we already have that this is a group under multiplication, an abelian group. And so from that fact, you know that there has to be a multiplicative identity because groups have identities. Also, it has to be commutative because it's an abelian group. And so remember, an integral domain is a commutative ring with unit that has no zero divisors. And so we have two of the three properties here, and this is the proof of the third property. Of course, I tend to emphasize the third property for integral domains because it's usually the hardest one to prove. The other theorem I prove is actually kind of interesting. It says that if you have a finite integral domain, then it's actually a field. So whenever you prove a theorem, there's always a question of whether or not the converse is true. Is every field, we just showed that every field was an integral domain, but there are integral domains that are not fields, namely the integers, because 2 doesn't have a multiplicative inverse in the integers. Its multiplicative inverse is 1/2, which is not an integer. But it turns out if your integral domain is finite, it must be a field. So in particular, this automatically tells you that in a finite commutative ring with a unit, it's either a field or you have to have zero divisors. And so let's look at the proof. So suppose you have a finite integral domain. Let's take a non-zero element. Let's define a function from the non-zero elements to themselves by left multiplication. By the way, the reason why we know this codomain is correct is because it's an integral domain. You actually know that if x is not 0, ax must also not be 0. Because if ax were 0, then congratulations, a is a zero divisor, contradicting the definition of integral domain. So left multiplication, that's where the fact that you don't have zero divisors is used. It's to claim that this codomain is actually non-zero elements of D. It's also used here. We proved this cancellation property. So since ax equals ay always implies x equals y, when a is non-zero, we actually know f is injective. So we have an injective function from a set to itself. It's a known fact that when you have a finite injective functions from a finite set to another finite set of the same size, that injective function actually has to be a bijection. This means that it has to be surjective. In particular, the preimage of the unit has to be non-zero, which means that there exists a b such that f of b is 1. In terms of the definition of f, that means a times b is 1. Congratulations, a has an inverse. So this is a very clever proof. I would not expect people to necessarily come up with this. But you see where the concept of finite is being used. I mean, the idea is that you have to try to solve this equation ax equals 1. And the trick on how they decide to do it is to instead recognize that instead of looking at ax equals 1, you look at the question ax equals y. Can you solve that in general? And normally if you have inverses, you already know that there should always be a unique solution, which means that the function, this function has to be a bijection. And then you just go back and check and realize, oh yeah, it has to be because it's injective and you're dealing with finite sets. So you could reverse engineer and see how you could have come up with this on your own. So looking at the finite rings we know so far, we only really know about Z mod NZ. When n is not prime, we already showed that there were zero divisors. When n is prime, it turns out it's actually always a field. We actually know this because we managed to prove that the non-zero elements form a group with respect to multiplication earlier in the course. And so that actually proves the result. And so the previous result tells us that, we already see this separation here into fields and zero divisors, and the theorem shows us that at least for finite rings, commutative rings with unit, this observation actually carries through, even for the finite rings we don't know exist. You're either always going to get one of these two cases. You're never going to get an integral domain that isn't a field. Of course, I'm sure you're wondering what other possible finite rings exist out there. Well, you're going to have to take, we will discuss ideals later in this course, but basically if you take a finite ring, well, you can take a finite ring, take the polynomial ring over it, and you quotient out by something called an ideal coming from an irreducible polynomial. This usually gives you a finite ring too. In particular, if you work with Z mod PZ, and you mod out by what's called an irreducible polynomial, you actually get a finite field. So that's something you learn in modern algebra too. That's usually important for certain applications, how to construct finite fields beyond just Z mod PZ. The other obvious constructions is to take matrices with coefficients in a finite ring. It turns out that gives you a finite ring, but this is obviously not commutative in general. So that's usually not the way to go if you're trying to create finite fields. And the other approach is to take direct products of rings. But this usually introduces zero divisors. Typically, you'll find. So we're not proving any of this. This is just side conversations for people who want to explore these concepts in the future in a second modern algebra course.